Hey guys, today we'll talk about the Hall effect. So Hall effect is when a current carrying semiconductor, suppose we have an n-type semiconductor, is placed in a magnetic field. The charge carrier here is the electrons because this is an n-type semiconductors. Then the charge carrier of the semiconductor experience a force in a direction perpendicular to both the magnetic field and the current. Suppose that we have a current carrying conductor, and of course current, if this is n-type semiconductor, then electrons are moving in this direction, electrons are moving in this direction, so current will be in that direction. So current is in that direction, electrons in this direction, so I-x is the direction of the current. So suppose that we will put this current carrying semiconductor in a magnetic field. So of course if we suppose that this is the direction of electron, so Vd or E. So Vd is the drift velocity of the electrons and E is the electron. So if we put this current carrying conductor in a magnetic field, and magnetic field is pointing out of the paper, so I'll take this out of the paper for this dot out of the paper, and I suppose that this out of the paper direction is Z direction, so I'll write Bz here. So by right hand rule, there will be a force which will act in the downward direction. So force will act in the downward direction, of course. So if this is your direction of the thumb, which is the direction of the electrons, and this is Bz for your finger with the thumb, so the middle finger will be the downward. So you can check at home, is it work or not. So it means that because when we put this current carrying conductor in a magnetic field, there will be a force acting on it, and this force, and with this force is acting downward direction, so this force is known as the Lorentz force. So because now there is a force acting, now there is a magnetic field here, so suppose this is the magnetic field here, because okay, so now the electron, there is a magnetic field act force on it, which is known as the Lorentz force. So because of this force, electron will deviate its path and it will accumulate to the down direction of the conductor. So this is the down direction. So suppose that electrons are accumulating here, here, and here, and because electrons are accumulating downside of the conductor, so there will be a potential difference which will develop across the conductor. So some positive ions are accumulating in this direction, so there will be a potential difference which will be created inside the conductor. So because of this positive ion, there will be a induced electric field or induced EMF will be generated inside a conductor, and we will say this induced EMF, Hall EMF, which is EH. Okay, so because of this magnetic field, there is an EMF which is generated across a semiconductor, which we say that Hall EMF. So after some times, this Lorentz force and this Hall force, which is Hall EMF, which is due to the Hall EMF, will these two forces will balance each other. So after some time, when the electron come this inside a semiconductor, these two forces, which is EH, which is the Hall force because of these positive ions, and this downward force, the Lorentz force, which I'm saying here is Fm, and for it should be Fh, sorry. So these two forces will be balance each other, and electron will move straight through the conductor. So after sometimes these two forces are balance each other, so I can write it here in this way, that Fm is equal to Fh. So so now what is Fm? So Fm is the Lorentz force, which is minus E. We know that what is the Lorentz force? E V cross B. And the force, what is the FH, Hall force, which is like FH is equal to E EH. This force is due to this Hall EMF or Hall force, and Fm is the Lorentz force. We all know from the high school it's minus E V cross B. So this V is Bz and V is Vd, so we will write it Vz and Vd, and here it is E into H. So now because these two forces are balance each other, so here we equate these two equations here, so E V into B. So there's a sign of these two are perpendicular to each other, velocity and the magnetic force. So VB sine of 90 is equal to EH. So this will be EVDB is equal to E. So E will be cancelled out, so we will have VD BZ here is equal to EH. So this is Hall EMF. It should be subscript. So here, okay. So we'll have the value of EH now. Hall EMF is EH is equal to VD BZ. So this will be the equation 1. Okay. We know that from the high school that current density is J is equal to NEVD. VD is the drift velocity and VD is equal to J by NE. Okay. Or we can say that VD is equal to current density is current per unit area and E. So, and what is the area here? Area is of course, you can see that this is the width and this is the height of the conductor. So we can say that area is W into T. So we can write that here, VD is equal to I by W into T